You're standing in the darkness, watching a single point of light drift across your screen. It's faint, almost invisible against the sea of stars. But something about its movement makes your breath catch. This isn't following the rules. This doesn't belong here. Veteran astronomers have been tracking it for weeks now, their calculations growing more urgent with each passing day. Because this visitor didn't form in our solar system. It came from somewhere else, somewhere unimaginably far away, carrying with it chemistry and secrets from a star system we'll never see. And now, after a journey measured in millions of years, it's racing toward the sun. In the final hours before closest approach, this interstellar wanderer known as 3I/Atlas will experience something no human instrument has ever witnessed up close, the moment when an object from beyond our cosmic neighbourhood confronts the raw power of our star. The heat will be merciless. The forces will be extreme. And whatever happens next will either reveal the mysteries locked in its ancient ice, or destroy them forever. If something extraordinary is going to happen, it's going to happen now. If you're here for the kind of cosmic events that happen once in a generation, the discoveries that change what we know about the universe, make sure you're subscribed and notifications are on. What unfolds with 3I/Atlas in these crucial days could give us our first real glimpse into how other star systems form, evolve, and send their messengers across the galaxy. This is history in the making, and you're watching it happen in real time. The clock on your screen reads 11:47 p.m, December 18th. Somewhere above you, beyond the clouds and city lights, beyond even the thin veil of Earth's atmosphere, something is falling toward the sun at 180,000 miles per hour. You refresh the tracking data one more time. The numbers update. Closest approach 14 hours. 30 minutes. This is what astronomers call perihelion, the moment when an orbiting object swings closest to our star. It happens all the time. Really. Comets do it. Asteroids do it. Even Earth does it every January. But this time is different, because the object racing toward tomorrow's rendezvous didn't come from the asteroid belt between Mars and Jupiter. It didn't form in the Kuiper belt beyond Neptune. It didn't even originate anywhere in our solar system. 3I/Atlas came from the stars. Think about that for a moment. The ice and rock currently hurtling toward the sun's embrace spent the last several million years, possibly tens of millions of years, drifting through the absolute emptiness between star systems, while human civilization rose and fell, while continents shifted and species evolved and went extinct. This object was travelling through a darkness so complete, so profoundly isolated, that the nearest star would have appeared as just another faint point in an unchanging sky. And then, by chance or fate or simply the mathematics of gravity, our sun reached out across the void and caught it. The discovery itself was almost accidental, the way most great cosmic finds tend to be. On January 6, 2024, the Atlas survey system in Hawaii flagged an unusual object moving through the constellation of Ursa Major. Atlas, the asteroid terrestrial impact last alert system, scans the entire visible sky every night, looking for anything that moves against the background stars. Most nights, it finds asteroids. Sometimes it catches comets. But the object designated C2024A3 Atlas immediately stood out for one simple reason: it was moving wrong. Not wrong in the sense of being broken or malfunctioning, but wrong in the way that tells astronomers they're looking at something extraordinary. The orbit was hyperbolic, a mathematical term that essentially means this thing is moving too fast to be gravitationally bound to the sun. It wasn't circling our star like a planet or even following the elongated ellipse of a typical comet. It was following a path shaped like an open curve, one that would bring it in from interstellar space, swing it once around the sun, and send it back out into the galaxy forever. Only 3 confirmed objects in human history have had orbits like this. The first was Oumuamua in 2017, that strange tumbling visitor that looked like nothing astronomers had ever seen, sparking theories ranging from dense cometary fragments to, more controversially, alien probes. The second was 2I/Borisov in 2019, which at least had the courtesy to look and behave like a normal comet, just one that happened to come from another star system. 3I/Atlas is the third, and it's behaving like neither of its predecessors. When astronomers calculated backward along its trajectory, they found something both beautiful and unsettling. Before the sun's gravity bent its path, 3I/Atlas was moving through interstellar space at roughly 20 kilometers per second, relative to the local standard of rest, the average motion of stars in our galactic neighbourhood. That velocity suggests it wasn't ejected violently from some distant solar system. Instead, it was probably born in the protoplanetary disk around another star, gently nudged into interstellar space by gravitational interactions with giant planets, and then set adrift to wander the galaxy for millions of years. Imagine being alone in the cosmic dark for that long. The star it once orbited, wherever that was, would have faded to invisibility within a few years of its ejection. For millions of years afterward, there would be no change, no reference point, no sense of time or motion, just the deep cold of space. Temperatures hovering around minus 400 degrees Fahrenheit, slowly pulling heat away from the object's core. Until now. As December 19th approaches, 3I/Atlas is experiencing something it hasn't felt since it left its home system warmth. Real, intense, life-altering warmth. At its closest approach, it will pass just 31 million miles from the sun's surface. That might sound like a safe distance. It's more than a third of the distance between Earth and the sun, but for a comet, it's intimate. It's close enough for the sun's radiation to heat the surface to over 300 degrees Fahrenheit. Close enough for ices that have been frozen solid for millions of years to suddenly boil away into space. Close enough for structural stresses that could tear the object apart. NASA's Solar Dynamics Observatory has already been repositioned. The European Space Agency's Solar Orbiter is standing by. Ground-based telescopes from Chile to Hawaii have cleared their schedules. Because here's the thing about perihelion, it's often when comets do something unexpected. The sudden heating, the intense gravitational forces, the rapid rotation it creates conditions where structure that seems solid can suddenly fracture, where hidden pockets of volatile material can explode outward, where an object that's been dormant for millions of years can suddenly wake up. And 3I/Atlas has already shown signs of waking up. In late October, observers noticed something unusual. The comet had brightened significantly, far more than models predicted it should at that distance from the sun. The increase wasn't gradual, it was sudden, like someone had flipped a switch. For a few days, 3I/Atlas was pumping out dust and gas at rates that suggested something had changed beneath its surface. Then, just as suddenly, it dimmed again. Outbursts like this aren't unheard of in comets, but they're supposed to happen to comets that have made many trips past the sun. Comets whose surfaces have been weathered and cracked by repeated heating and cooling cycles. 3I/Atlas is on its first pass. Whatever caused that October outburst came from the original structure of the object itself, characteristics it brought with it from another star system. Which raises the question that has astronomers around the world checking their instruments every few hours if it did that back in October, when it was still relatively far from the sun. What's it going to do on December 19th? The countdown stands at less than 12 hours now. 12 hours until we find out if this interstellar wanderer survives its closest brush with our star, or if the forces at perihelion tear it apart. 12 hours until we see what secrets, chemical, structural, perhaps even biological, have been locked in its ancient ice. 12 hours until 3I/Atlas either becomes one of the most studied objects in astronomical history, or vanishes in a cloud of debris that will disperse across millions of miles before we can learn what it was made of. But before we can understand what might happen at perihelion, we need to understand what makes this visitor so different from anything else we've ever observed. Because the more data astronomers gather, the clearer it becomes 3I/Atlas isn't playing by the rules we thought governed interstellar objects. When Oumuamua blazed through our solar system in 2017, it arrived with all the subtlety of a cosmic alarm bell. Astronomers barely had time to notice it before it was gone, discovered on its way out, already past the Sun and accelerating toward the outer solar system. By the time telescopes swung around to capture images, it was just a faint dot of light, tumbling end over end at a rate that suggested something deeply unusual about its shape. The data pointed to an object so elongated, roughly 10 times longer than it was wide, that nothing like it had ever been seen in our solar system. People called it everything from a space cigar to, less scientifically, a cosmic alien probe. The theories got wilder when astronomers noticed it was accelerating away from the Sun slightly faster than gravity alone could explain. Something was pushing it, outgassing from sublimating ice. Probably. But no one could detect the gas itself, and the mystery only deepened. Then came 2I/Borisov in 2019, and astronomers breathed a collective sigh of relief. Here, finally, was an interstellar visitor that made sense. It looked like a comet. It acted like a comet. It had a visible coma, that fuzzy cloud of gas and dust that surrounds an active comet's nucleus. Spectroscopic analysis showed water vapour, carbon monoxide, and dust composition that matched comets born in our own solar system. If anything, Borisov was almost disappointingly normal, just a regular comet that happened to come from somewhere else. So when 3I/Atlas appeared in January 2024, astronomers had a mental framework ready. It would be either strange like Oumuamua or normal like Borisov. Binary choice. Weird or familiar? 3I/Atlas chose option 3 both, somehow, at the same time. Start with the basics, the orbit itself. When you calculate a comet's orbit, you get a number called orbital eccentricity. A perfect circle has an eccentricity of 0. Earth's orbit, which is nearly circular, has an eccentricity of 0.017. A long ellipse, like Halley's Comet, might have an eccentricity of 0.967. But once you cross 1.0, you're in hyperbolic territory. The object isn't bound to the Sun, and it's leaving forever. Oumuamua had an eccentricity of 1.20. Borisov came in at 3.36, moving so fast that gravity could barely bend its path before it shot back out into space. 3I/Atlas. Its eccentricity is approximately 1.00057. Read that again. It's barely hyperbolic. Just barely. This object is moving through our solar system at almost exactly escape velocity, the minimum speed needed to break free of the Sun's gravity. Slow it down by a fraction of a percent, and it would have been captured, doomed to orbit our star for billions of years. Speed it up slightly, and it would have zipped through even faster than it already is. What are the odds of that? What kind of cosmic accident sends an object on an interstellar trajectory at precisely the speed needed to make its orbit just barely unbound? Dr. Darrell Seligman, an astronomer at Cornell University who studies interstellar objects, noted in an October 2024 interview with Sky and Telescope that such low eccentricity hyperbolic orbits are statistically unusual among the interstellar population we'd expect. Most objects ejected from other solar systems should be moving much faster through interstellar space, not dawdling at the minimum speed required to remain unbound. It gets stranger when you look at how it's behaving. Unlike Oumuamua, which showed no visible coma and left astronomers guessing at its composition, 3I/Atlas has been actively outgassing since late summer. Observations from the European Southern Observatory's Very Large Telescope in Chile detected clear spectral signatures of dust and gas surrounding the nucleus, classic comet behaviour. Good. Normal. Except the pattern of that activity doesn't match what models predict. Typical comets brighten gradually as they approach the Sun, following a predictable curve based on how quickly ice sublimates at different temperatures. You can actually write an equation for it. Brightness increases with the inverse square of the distance from the Sun, modified by the comet's size and composition. Astronomers have been using variations of this equation since the 19th century, and it works. It's reliable. 3I/Atlas brightened too quickly in September, then plateaued in early October, then suddenly surged brighter in late October, that mysterious outburst we mentioned earlier, before settling back down. It's as if the comet can't decide whether it wants to be active or dormant, as if different regions of its surface are waking up at different times, responding to the sun's heat in ways that standard comet models don't predict. Could it be tumbling, rotating in a complex way that exposes different faces to sunlight at irregular intervals? Possibly, but observations of its light curve the way its brightness changes over time haven't revealed the clear periodic variations you'd expect from a tumbling object. It's bright, then it's dimmer, then it's brighter again, but without an obvious pattern. Dr. Matthew Knight, a comet specialist at the US Naval Academy, pointed out in a November preprint paper that 3I/Atlas's activity profile suggests either a heterogeneous surface composition or an unusual internal structure, perhaps both. Translation: this thing is made of different materials in different places, mixed together in ways we're not used to seeing, which, when you think about it, makes sense. It formed around a different star, possibly in a protoplanetary disk with a different temperature gradient, different available elements, maybe even different ice to rock ratios than what we're familiar with. Here's where it gets really interesting. When spectroscopes at the Keck Observatory in Hawaii analysed the gas streaming off 3I/Atlas in early November, they detected carbon monoxide, lots of it, more CO relative to water ice than most solar system comets produce. That's not unheard of. Some comets from the outer reaches of our own Oort cloud show similar chemistry. But combined with the unusual activity pattern and the barely hyperbolic orbit, it's another piece of a puzzle that doesn't quite fit together. And then there's the size question. Based on brightness and assumptions about how reflective the surface is, astronomers estimate 3I/Atlas's nucleus is somewhere between 1 and 3 kilometers across. But that's a huge range. Double the diameter, and you've got 8 times the volume, 8 times the mass. Is this a small, bright object or a larger, darker one? Without knowing the exact reflectivity, what astronomers call albedo, we can't be sure. Why does size matter? Because it determines how much heat the sun can pump into the core, how quickly structural stresses build up, and ultimately, whether the object is likely to survive perihelion intact or break apart under the strain. Borisov, for reference, was about 400 meters across, roughly half the size of the smallest estimate for 3I/Atlas. It survived its perihelion just fine, passing 300 million kilometers from the sun without incident. But Borisov never got as close as 3I/Atlas is about to get. And size isn't everything. Composition, structure, rotation rate, they all factor into whether a comet holds together or fractures. So we're left with an object that defies easy categorization. It's acting like a comet, but not behaving the way comets typically behave. It's on an escape trajectory, but moving at the minimum possible speed for that trajectory. It's brightening and dimming in patterns that don't match standard models. And it's about to experience temperatures and gravitational stresses that would destroy a weaker object or reveal hidden structure in a stronger one. There's a term astronomers use when dealing with objects like this. Objects that sit at the boundary between categories and challenge the neat boxes we've created. Transitional. 3I/Atlas might be transitional between comet and asteroid, between bound and unbound, between active and dormant, or it might be something we don't have a category for yet, something that only makes sense in the context of the star system where it formed, but we won't know until the sun turns up the heat and forces it to show its true nature. And that moment, the moment when millions of years of frozen chemistry meets the raw power of solar radiation, is less than 8 hours away now. The question isn't just what 3I/Atlas is. The question is, what's it going to become when the pressure is on? Imagine you're standing on the surface of 3I/Atlas right now, not in a spacesuit that wouldn't help, but as a disembodied observer, watching the universe from the perspective of this ancient traveller. For millions of years, the view has been essentially unchanging stars scattered across an infinite black canvas, no brighter in one direction than another, cold, silent, still. But in the past few months, one star has been growing brighter, slowly at first, then faster. What began as just another point of light is now a blazing disk, dominating the sky ahead, pumping heat into rock and ice that haven't felt warmth since this object left its birth system. The surface beneath you dark, irregular, pockmarked with craters and fissures is beginning to stir. Tiny geysers of vapour are erupting from cracks where sunlight has penetrated deep enough to reach buried pockets of frozen gas. The ice isn't melting. At these pressures, it's sublimating, going directly from solid to vapour without ever becoming liquid. This is what perihelion feels like from the inside. And it's about to get much, much more intense. At 31 million miles from the Sun, 3I/Atlas will experience solar radiation roughly 10 times stronger than Earth receives. That might not sound catastrophic after all. Mercury endures conditions far worse, orbiting at an average distance of just 36 million miles and getting hit with radiation about 11 times what we feel on Earth. But Mercury is a solid ball of iron and rock, baked and hardened over 4.6 billion years of continuous solar exposure. Its surface temperature swings from 800 degrees Fahrenheit on the day side to minus 290 degrees Fahrenheit at night, and it doesn't even flinch. 3I/Atlas is not Mercury. It's a loosely bound collection of ice, rock, and dust, more like a cosmic snowball than a solid sphere. And it's never experienced anything like this before. The physics of what happens at perihelion is both beautiful and brutal. As solar radiation penetrates the surface, it doesn't heat everything evenly. Dark regions absorb more energy than bright ones. Cracks and fissures channel heat deeper than smooth areas. The result is thermal stress, different parts of the object expanding and contracting at different rates, creating internal pressures that can exceed the tensile strength of the material itself. Think of it like taking a frozen dinner out of the freezer and putting it directly into a hot oven. The outside heats up fast while the inside is still frozen solid. The temperature difference creates stress. Sometimes that stress releases harmlessly. Sometimes it shatters the container. For comets, we've seen both outcomes sometimes in the same object. Take Comet Linear, officially designated C1999S4. In July 2000, as it approached perihelion at a distance of about 70 million miles from the Sun, more than twice as far as 3I/Atlas will get, astronomers watched it simply fall apart. Not in one catastrophic explosion, but in a slow-motion disintegration that took weeks. The nucleus fractured into dozens of pieces, each piece then fracturing further, until what had been a single kilometre-sized object became a dispersing cloud of house-sized boulders, then car-sized chunks, then gravel, then dust. By the time it reached perihelion, there was nothing left but a faint streak of debris. Or consider Comet Ison, the comet of the century that wasn't. In November 2013, Ison dove toward the Sun on a trajectory that would take it just 730,000 miles above the solar surface, almost grazing the actual atmosphere of our star. Predictions ranged from "it'll be the brightest comet in decades" to "it won't survive." Spoiler, it didn't survive. Ison entered perihelion as a solid object about a mile across and emerged as a faint smudge of dust that faded from view within hours. The Sun had simply vaporized it. But here's the thing. Not all comets die at perihelion. Some get stronger. Comet Lovejoy, which made a death-defying pass just 87,000 miles above the Sun's surface in December 2011, was expected to vaporize completely. Astronomers watched it disappear behind the Sun, waited for it to emerge on the other side. And there it was, not only intact, but brighter than before, trailing a magnificent tail of dust and gas that stretched across millions of miles. Something about its internal structure, the way its ice and rock were bound together, allowed it to withstand temperatures exceeding 3,600 degrees Fahrenheit and gravitational forces that should have torn it apart. So which fate awaits 3I/Atlas, disintegration like linear, vaporization like Ison, triumphant survival like Lovejoy? The answer depends on factors we can't directly measure from 31 million miles away. How much of the nucleus is ice versus rock? Are there large, solid boulders embedded in the ice? providing structural support, or is it more like a loosely packed rubble pile, held together by little more than its own weak gravity as the rotation stabilizing it, or creating additional stress through centrifugal force? Dr. Quanxi Ye, an astronomer at the University of Maryland who specializes in cometary behavior, published a risk assessment for 3/Atlas in early December. His analysis, based on brightness variations and outgassing patterns, suggests the nucleus has already shed at least some surface material. Those October outbursts we mentioned earlier might have been small-scale fracturing events. The object is under stress, Ye noted in an interview with New Scientist. Whether that stress leads to catastrophic fragmentation or controlled outgassing depends entirely on internal properties we can't observe directly. There's also the gravitational factor. At closest approach, 3I/Atlas will be well outside the Roche limit, the distance at which tidal forces from the Sun would literally rip it apart through differential gravity. The Roche limit for an icy object near the Sun is about 550,000 miles. At 31 million miles, 3I/Atlas will be safely beyond that threshold, but safely is relative. Even at this distance, the Sun's gravity creates measurable tidal stress, trying to stretch the object slightly along the Sun-comet axis. For a solid, coherent body, this stress is negligible. For a weakly bound rubble pile, it could be the final straw that triggers fragmentation. And then there's the rotation. We don't yet know how fast 3I/Atlas is spinning, but rotation rate can make the difference between survival and destruction. Spin too fast, and centrifugal force works against the already weak gravity holding the object together. Spin too slow, and you don't get the stabilizing gyroscopic effect that helps keep irregular objects from tumbling chaotically. Comet 67P/Churyumov-Gerasimenko, which the European Space Agency's Rosetta probe orbited for 2 years, rotates once every 12.4 hours a rate that seems to be common among larger comets. If 3I/Atlas is rotating much faster or slower than that, it could indicate unusual structural properties. What we know for certain is this perihelion is the great revealer. It strips away surface layers. It exposes internal structure. It forces objects to show whether they're solid or fragile, ancient or recently formed, pristine or weathered. Every comet that survives perihelion comes out changed, sometimes subtly, sometimes dramatically. And for an interstellar visitor carrying chemistry from another star system, those changes could tell us things we have never learned before about how planetary systems form in distant corners of the galaxy. The countdown now reads just over 4 hours. 4 hours until 3I/Atlas reaches the point of maximum stress, maximum heating, maximum revelation. Telescopes are locked on target. Spectrographs are ready to capture whatever gases get released. High-speed cameras will record any sudden brightening or fragmentation events. But there's another element to this story we haven't fully explored yet. Something that happened back in October, when 3I/Atlas was still far enough from the Sun that it should have been quiet, dormant, inactive. That mysterious outburst that defied predictions and suggested something volatile lurking beneath the surface. Because if that was just a preview, a minor rumble before the main event, October 28th, 2024, an astronomer at the Lowell Observatory in Arizona pulls up the latest brightness measurements for 3I/Atlas and stops mid-sip of coffee. The numbers don't make sense. Yesterday, the comet was magnitude 12.3 visible only through decent-sized telescopes. Today it's reading 10.8. That's not a typo. That's not measurement error. That's a brightness increase of roughly 400% in 24 hours. Something inside 3I/Atlas had woken up. Outbursts sudden, dramatic increases in a comet's brightness are one of the most puzzling phenomena in planetary science. They happen when a comet suddenly starts ejecting far more dust and gas than normal, sometimes brightening by factors of hundreds or even thousands within hours. And here's the unsettling part: we still don't fully understand what triggers them. The most famous example in recent history is Comet 17P/Holmes. On October 24, 2007, Holmes was a faint, unremarkable periodic comet that most amateur astronomers had never bothered to observe. It was magnitude 17, so dim you'd need a serious telescope and perfect conditions just to spot it. Then, over the span of just 42 hours, it exploded in brightness by a factor of nearly 400,000. Suddenly it was magnitude 2.8 visible to the naked eye, brighter than most stars in the night sky. Its coma, that cloud of gas and dust, expanded so rapidly that within weeks it was larger than the Sun in diameter. Even though the solid nucleus at its centre was only about 2 miles across, what caused it, we still don't know for certain. The leading theory is that a large cavity of frozen carbon monoxide or nitrogen, buried beneath the surface, was suddenly exposed to sunlight. These supervolatile ices sublimate at much lower temperatures than water ice. When sunlight hit them, they exploded outward with tremendous force, punching through the overlying material and dragging vast amounts of dust along with them. The comet essentially burped violently. But here's what made Holmes particularly strange. It was already a known comet, one that had orbited the Sun many times before. It had passed perihelion in May 2007, 5 months earlier, without incident. Then, on its way back out toward the outer solar system, far from the Sun where it should have been getting quieter, it exploded. The outburst happened at a distance of 2.4 astronomical units from the Sun, about the same distance as the asteroid belt. By all logic, it should have been dormant. Now consider 3I/Atlas's October outburst. When it happened, the comet was approximately 1.6 astronomical units from the Sun closer than Holmes was, but still well outside the traditional frost line, where water ice begins to sublimate vigorously. At that distance, solar heating should have been causing steady, gradual activity, not a sudden surge. Dr. Michael Kelly at the University of Maryland, who has spent years studying cometary outbursts, analysed the October event using data from multiple observatories. In a preliminary paper posted in early November, he noted that the outburst displayed characteristics consistent with either a discrete eruptive event from subsurface volatiles, or possibly rotational exposure of a previously shadowed active region. In other words, either something exploded from inside the comet, or the comet rotated in just the right way to suddenly expose a particularly icy patch to direct sunlight. Both explanations have problems. If it was an internal explosion, what was the trigger 3I/Atlas has never been this close to the Sun before it's on its first pass through the inner solar system. There's been no thermal cycling, no repeated heating and cooling to create internal pressure build-ups. The material in this comet has been frozen solid for millions of years, yet something caused a pocket of it to suddenly release. If it was rotational exposure, that implies the comet has dramatically uneven composition patches of volatile rich material next to patches of stable, inactive material. That's not impossible. The nucleus of Comet 67P, which Rosetta studied extensively, showed significant compositional variations across its surface. But 67P is a Jupiter family comet that's made hundreds of trips past the Sun. It's had time to develop an uneven, weathered surface. 3I/Atlas should still be relatively pristine, unless it's not. There's a third possibility that researchers are beginning to consider. Maybe 3I/Atlas experienced significant activity before it ever entered our solar system, perhaps during its formation, or during its ejection from its home system, or during some close encounter with another object during its millions of years wandering through interstellar space. Any of those events could have created internal fractures, exposed fresh volatile material, or left it in a structurally weakened state. We think of interstellar space as empty and unchanging, but it's not a perfect vacuum. There are trace amounts of gas, microscopic dust particles, even occasional encounters with hydrogen clouds. Over millions of years, those small interactions add up. They could erode surfaces. They could impact the object and create cracks. They could alter the very structure of the nucleus. When NASA's Stardust probe flew past Comet Wild 2 in 2004 and collected dust samples from its coma, scientists expected pristine material ancient building blocks of the solar system, unchanged since formation. What they got surprised them. The samples contained minerals that had been heated to over 2000 degree F, far hotter than anything that should exist in the cold outer solar system where Wild 2 formed. The explanation? Those minerals must have formed close to the infant sun, then been transported outward by turbulent mixing in the early protoplanetary disk. Comets, it turned out, contain material from wildly different environments, all jumbled together. Could 3I/Atlas be similarly heterogeneous? But with the added complexity of forming around a different star, its protoplanetary disk might have had different temperature gradients, different mixing patterns, different available elements. The outburst could be revealing that internal diversity, a pocket of material that responds differently to solar heating than the surrounding material. What makes the October event even more intriguing is what happened afterward. The brightness faded again. Not instantly, but over the course of about a week. 3I/Atlas dimmed back down close to predicted levels. Whatever caused the surge in activity had either exhausted itself or been covered over. Imagine a geyser on Earth that erupts once, forcefully, then goes dormant. The water is still there underground. The heat is still there. But the pathway to the surface has been blocked perhaps by the debris from its own eruption. That raises an uncomfortable question. Could it happen again? History suggests yes. Comet Holmes had actually outburst once before, back in 1892 during its discovery apparition. It brightened suddenly, was discovered, then faded. It came back around in 1899, 1906 and so on, orbiting peacefully for over a century before the massive 2007 event. Some comets seem to be prone to outbursts, harbouring reservoirs of volatile material that can be triggered repeatedly under the right conditions. If 3I/Atlas has similar reservoirs, and the October event suggests it might then perihelion is when they're most likely to erupt again, the sun's heat will be at maximum intensity. Any remaining pockets of super volatile ices will be under maximum stress. Structural weaknesses will be maximally exposed. Dr. Colin Snodgrass, who leads the European Southern Observatory's Comet Observation Programme, put it bluntly in a December interview with Astronomy magazine. We're watching for the other shoe to drop. October was a warning. Perihelion is when we find out if that was the only shoe, or if there are more waiting. There's precedent for this. Comet Schwarzmann-Wachmann 3, which we mentioned earlier, didn't just fragment once it had been experiencing minor outbursts for decades before its final, catastrophic breakup in 1995. Each outburst weakened the structure a little more, created new fractures, exposed new volatile material. By the time it reached perihelion, it was ready to fall apart, and it did, splitting into dozens of fragments that dispersed along its orbital path. So as 3I/Atlas approaches those final hours before closest approach, astronomers aren't just watching for whether it survives. They're watching for signs of another outburst, a sudden surge in brightness, a spike in gas production, a change in the dust emission pattern. Any of those could be the signal that something fundamental is happening beneath the surface, that millions of years of frozen chemistry are suddenly being unlocked. And if there is another outburst, if those volatiles do erupt during perihelion, we'll get something rare and precious, a direct spectroscopic snapshot of material from another star system. At the moment it's being released, the gases won't have time to disperse, the dust won't have time to spread out. We'll be capturing the raw chemistry of an alien world, preserved for millions of years, revealed in an instant. But to understand what that chemistry might tell us, what secrets are locked in the ice and rock of 3I/Atlas, we need to look at what comets are actually made of, and why an interstellar visitor's composition matters so much. When you break a comet down to its fundamental components, you're essentially looking at a time capsule from the birth of a solar system. Not our solar system, or in this case, possibly not, but a solar system. The ice, the rock, the trace organic molecules, they're all remnants of the swirling disk of gas and dust that collapsed to form a star and its planets roughly 4.6 billion years ago. Water ice makes up the bulk of most comets we've studied, usually around 80% of the volatile material. That makes sense. Oxygen is the third most abundant element in the universe after hydrogen and helium, and hydrogen is number one. Put them together in the cold outer regions of a forming solar system, and you get lots of water ice. Simple chemistry. Universal physics. But here's where it gets interesting. The ratio of different molecules in a comet tells you about the specific conditions where it formed. Temperature, mainly. How far from the young star was the material when it froze? What was the pressure? Were there shock waves from stellar winds compressing the disk? Every comet carries a chemical fingerprint of its birthplace. When spectroscopes at the Gemini Observatory in Hawaii analyse light passing through 3I/Atlas's coma in early November, they detected something unexpected. The carbon monoxide to water ratio was high, not impossibly high, but higher than most comets from our own solar system show. Carbon monoxide CO is what chemists call a supervolatile. It freezes at much lower temperatures than water, around minus 340 degrees Fahrenheit, compared to water's 32 degrees Fahrenheit. You only get significant amounts of CO ice if material froze in the very cold outer regions of a protoplanetary disk. Beyond where the giant planets formed, most solar system comets have CO to water ratios around 5%. That's the baseline we're used to. 2I/Borisov, our previous interstellar visitor, measured around 70% CO relative to water, shockingly high, suggesting it formed in an extremely cold region of its home system. Initial measurements of 3I/Atlas put it somewhere in between, with estimates ranging from 15–30% CO, still elevated compared to typical solar system comets, but not as extreme as Borisov. What does that tell us potentially? That 3I/Atlas formed in a moderately cold region of its protoplanetary disk, farther out than where Neptune-like planets would orbit, but not in the absolute frigid outer reaches where Borisov likely originated. It's a Goldilocks composition, not too hot, not too cold, but distinctly different from the average. But there's a complication. Carbon monoxide isn't just a passive tracer of formation conditions, it's also incredibly reactive when exposed to cosmic rays. Over millions of years in interstellar space, high-energy particles from distant supernovae and other sources constantly bombard any object not protected by a star's magnetic field. Those particles can break chemical bonds, create new molecules, alter the surface chemistry. The CO we're detecting now might not reflect the original composition. It could be depleted from what it was when 3I/Atlas left its home system. Or it could be enhanced if UV radiation from distant stars broke down more complex molecules into simpler ones like CO. Dr. Martin Cordner at NASA's Goddard Space Flight Center, who led the Gemini observations, acknowledged this uncertainty in a December presentation at the American Astronomical Society meeting. We're measuring present-day composition, not necessarily primordial composition. Interstellar processing could have significantly altered the chemistry we're seeing. Translation. The comet we're observing now might be chemically different from the comet that began its journey millions of years ago. Then there's the dust. When sunlight scatters off particles in a comet's coma, the colours reveal information about grain size and composition. Observations from the European Space Agency's optical ground station in Tenerife showed that 3I/Atlas's dust has a slightly reddish colour, similar to many solar system comets, but with subtle differences in the spectrum that suggest the grains might be coated with organic compounds. Not life don't get excited, but complex carbon-based molecules formed by chemical reactions in the cold vacuum of space. These organic compounds, technically called tholins, are created when simpler molecules like methane, ethane, and nitrogen are exposed to UV radiation. They're gummy, sticky substances that coat dust grains and give them that characteristic reddish-brown colour. We see them on Pluto. We see them on Saturn's moon Titan. We see them in the outer reaches of our solar system. And now, apparently we're seeing them on a visitor from another star system. What's fascinating is that this suggests similar chemistry happens around other stars. The building blocks are the same. The processes are the same. The results are similar. It's a reminder that the laws of physics and chemistry don't stop at the edge of our solar system. Carbon behaves the same way everywhere. Water freezes at the same temperature whether you are orbiting our sun or a star 50 light-years away. But similar doesn't mean identical. When the Atacama Large Millimeter Array in Chile, one of the most powerful radio telescope networks on Earth, pointed towards 3 I/Atlas in late November, it was searching for specific molecular signatures that might reveal subtle differences. Radio observations can detect molecules that optical telescopes miss hydrogen cyanide, methanol, formaldehyde, ammonia. Each of these molecules has a unique radio fingerprint, a specific frequency at which it absorbs and emits radiation. The preliminary results, still being analysed, show traces of hydrogen cyanide HCN in the coma. That's normal for comets. HCN is common in the cold molecular clouds where stars form, and it gets incorporated into icy bodies early in a solar system's history. But the isotopic ratio, the relative abundance of different versions of hydrogen and nitrogen atoms in the molecule, appears slightly different from solar system averages. Not wildly different, but measurably so. Isotopes are like different flavours of the same element. Normal hydrogen has one proton. Deuterium, a heavier isotope, has a proton and a neutron. Both are hydrogen chemically, but they behave slightly differently in reactions, and they form under different conditions. The deuterium to hydrogen ratio in water ice can tell you about the temperature and radiation environment when that ice formed. In solar system comets, that ratio is typically around 3 parts deuterium per 10,000 parts hydrogen, written as 3 bub to 10^4. If 3 I/Atlas's deuterium ratio is different, and early hints suggest it might be that's evidence of formation under different conditions. Maybe its parent star had a different deuterium abundance. Maybe the protoplanetary disk was irradiated differently by nearby massive stars. Maybe the timescale of formation was longer or shorter, allowing different isotopic fractionation processes to dominate. These are subtle differences, the kind that require painstaking analysis to confirm, but they matter, because if we can measure the isotopic composition of an interstellar comet with precision, we're essentially doing geology, or rather, cosmochemistry on a world we'll never visit, orbiting a star we'll never see. We're reading the chemical autobiography of an object that formed before human civilization existed, possibly before complex life on Earth existed. And there's one more piece of the puzzle that has researchers particularly intrigued: the sodium emission. In mid-November, observers at the European Southern Observatory noticed a faint but distinct sodium line in 3 I/Atlas's spectrum, a yellow glow at 589 nanometers wavelength that indicates sodium atoms are being released from the nucleus. Sodium isn't usually a major component of comets. It's present in trace amounts, locked up in minerals within the rocky component. Seeing it in emission suggests either the nucleus has an unusually high sodium content, or something is efficiently releasing sodium from minerals that would normally keep it locked away. Dr. Cyril Oppitum, who led the ESO observations, noted in a preliminary report that the sodium emission intensity is comparable to what we see in some Jupiter family comets during their most active phases, which is unexpected for an object on its first perihelion passage. In other words, 3 I/Atlas is releasing sodium at rates you'd normally only see in comets that have been heated and processed by multiple trips past the Sun. Why does an interstellar visitor, on its first solar encounter, behave like a seasoned veteran of the inner solar system? Is it compositionally different, richer in sodium-bearing minerals? Is its structure different, more porous, allowing heat to penetrate deeper and release trapped elements more efficiently? Or did something happen during its interstellar journey that pre-processed its surface in ways we don't yet understand? These questions are more than academic curiosities. They're probes into how planet formation works across the galaxy. If 3 I/Atlas's chemistry is substantially different from solar system norms, it suggests that the star system where it formed had different initial conditions, perhaps a different abundance of heavy elements, a different disk structure, different dynamics during the planet formation era. But if its chemistry is fundamentally similar, That suggests planet formation follows universal patterns, with only subtle variations from system to system. We're about to get the most definitive answers we've ever had, because at perihelion, when the sun's heat is at maximum intensity, 3I/Atlas will release gases and dust at rates far higher than anything we've measured so far. Every spectrograph in the world that can see it will be recording. And if the nucleus does fragment, if structural failure exposes fresh material from the interior, we'll get something unprecedented, a direct look at pristine chemistry from another star system, material that's been shielded from radiation and processing, locked away in the core for millions of years. But fragmentation isn't a simple on-off switch. Comets don't just hold together or fall completely apart. The process is complex, progressive, sometimes violent, sometimes gradual. And the warning signs, if they exist, are what astronomers are searching for right now. Picture this: you're watching through a telescope as a comet approaches the sun, and suddenly you notice something odd. Where there was one bright point yesterday, now there are two, then three, then a string of glowing fragments, each trailing its own tail of dust and gas, spreading out along the orbital path like pearls on a broken necklace. This isn't science fiction. It's exactly what happened to Comet Shoemaker-Levy 9 in July 1994, except in that case the comet wasn't approaching the Sun, it was approaching Jupiter. In July 1992, 2 years before the famous collision, Shoemaker-Levy 9 passed within 25,000 miles of Jupiter's cloud tops, well inside the planet's Roche limit. Tidal forces, the difference in gravitational pull between the near side and far side of the comet, literally ripped it into at least 21 distinct pieces. Astronomers watched those fragments drift apart over the following months, each piece continuing along essentially the same orbit, until they slammed back into Jupiter in a series of spectacular impacts that left dark scars on the planet, visible even through backyard telescopes. That was tidal fragmentation gravity doing the work. But there's another way comets come apart, one that's potentially more relevant to 3I/Atlas thermal fracture. Comet Schwassmann-Wachmann 3 had been a quiet, predictable visitor since its discovery in 1930. Every 5.4 years it would swing through the inner solar system, brighten a bit, fade again, and head back out. Routine. Then in 1995 something changed. Instead of one nucleus, observers started seeing multiple components. By 2006, when the comet made its next perihelion passage, it had fractured into more than 60 identifiable pieces, scattered along a debris trail stretching over 1 million miles. The European Space Agency's Rosetta spacecraft, then on its way to rendezvous with Comet 67P, was redirected to fly past some of the larger fragments, capturing close-up images of the breakup in progress. What those images revealed was fascinating and slightly terrifying. The fragments weren't clean breaks, like someone had cut the comet with a knife. They were jagged, irregular, surrounded by clouds of smaller debris. Some pieces were still connected by tenuous bridges of material, slowly stretching and tearing. Others had clearly separated days or weeks earlier and were now tumbling independently, each rotating at different rates. The whole scene looked less like a single object breaking apart and more like a loosely bound pile of rock slowly falling apart under stress it could no longer withstand. That's the key insight: most comets aren't solid objects. They're rubble piles, collections of smaller chunks held together by a combination of weak gravity and ice acting like glue. When that ice sublimates away, when thermal expansion creates cracks that propagate through the structure, when rotation speeds up due to outgassing jets acting like tiny rocket engines, any of those factors can push the object past its structural limit. And here's the unsettling part: fragmentation doesn't always happen suddenly. Sometimes it's progressive. Comet 73P/Schwassmann-Wachmann 3, a different comet than the one we just discussed, despite the similar name, showed clear evidence of this progressive breakup. When it was first observed fragmenting in 1995, careful analysis of old photographs revealed that small pieces had actually been breaking off since at least 1970, maybe earlier. The comet had been slowly disintegrating for decades, shedding material bit by bit until finally, in 1995, the main nucleus split into larger, more obvious fragments. By 2006, those fragments had split further, and some of those subfragments had split again. The entire object was coming apart in stages, like a building demolition in extreme slow motion. Could 3I/Atlas be experiencing something similar right now? There are signs that make astronomers wonder. The October outburst we discussed earlier, that sudden 400% brightness increase, could have been more than just a gas release. Dr. Zdeněk Šekanina, a comet fragmentation expert at NASA's Jet Propulsion Laboratory, has analysed dozens of comet outbursts over his career, and he's found that many of them are associated with small-scale fragmentation events. When you see a rapid brightening followed by an extended fading, he wrote in a 2008 review paper, you're often looking at the signature of a discrete chunk separating from the main nucleus. The brightening is from fresh ice being exposed. The fading is that new surface getting covered with dust again. If that's what happened to 3I/Atlas in October, it would mean the nucleus has already lost at least some structural integrity. A piece broke off, maybe just a boulder-sized chunk, maybe something larger and exposed fresh, active material. That doesn't necessarily mean the whole thing is coming apart, but it does indicate the structure is under stress. Then there's the light curve. The pattern of brightness changes over time. When astronomers plot 3I/Atlas's brightness against time, the graph doesn't show a smooth curve. It's bumpy, irregular, with unexpected dips and rises that don't match simple models of a rotating nucleus with stable active regions. Those irregularities could be noise in the data, differences in how various telescopes measure brightness. Or they could be real variations caused by the nucleus changing shape, losing pieces, or exposing new surfaces as material breaks away. Dr. Jianyang Li at the Planetary Science Institute has been studying the morphology, the shape and structure of 3I/Atlas's coma using high-resolution images from the Hubble Space Telescope. While Hubble can't resolve the nucleus itself at this distance, it can see the inner coma in exquisite detail. And what Li has found is intriguing. The coma isn't perfectly symmetric. There are subtle jets and streamers pointing in specific directions, suggesting localized active regions on the nucleus. But those jets seem to be changing position between observations taken days apart. Either the nucleus is rotating in a complex way, tumbling rather than spinning smoothly, or the active regions themselves are moving as material breaks off and exposes new areas. We're seeing dynamical changes on timescales of days. Li noted in a December conference presentation, that's not what you typically see in a structurally stable comet nucleus. What would fragmentation look like if it happens at perihelion? That depends on how catastrophic it is. Best case scenario, small-scale shedding. The nucleus loses some surface material. Maybe a few house-sized boulders break off. But the main body remains intact. We'd see a temporary brightness spike as fresh ice gets exposed. Then activity would settle back down. The comet would survive, though slightly smaller and potentially more active than before. Middle scenario, partial fragmentation. The nucleus splits into a few large pieces, think 2 to 5 major fragments that remain relatively close together, continuing along similar orbits. Each fragment would have its own coma and tail, creating a spectacular visual display. This is what happened with Comet West in 1976, which split into 4 pieces during perihelion, but remained visible for weeks afterward, creating one of the most beautiful comets of the 20th century. Worst case scenario, catastrophic disintegration. The entire structure comes apart into hundreds or thousands of pieces, most too small to track individually. The nucleus essentially dissolves into a cloud of debris that quickly spreads out and fades from view. This is what happened to Comet Ison in 2013 and Comet Linear in 2000. One day you're tracking a solid object. The next day there's nothing but a fading smudge of dust. Which outcome is most likely for 3I/Atlas? The honest answer is we don't know. We don't have enough information about its internal structure, its rotation rate, or its precise composition. What we do know is that the conditions at perihelion will test whatever structural integrity it has. The thermal stress will be maximum. The gravitational gradient, though not tidal breakup level, will be significant. And if there are any existing cracks, any weak points in the structure, any remaining pockets of super volatile ices ready to explode, this is when they'll make themselves known. There's actually a formula astronomers use to estimate fragmentation risk, developed by studying hundreds of comet perihelion passages over the years. It factors in perihelion distance, estimated nucleus size, approach velocity, and activity level. When researchers plug in 3I/Atlas's parameters, they get an ambiguous result. The risk isn't negligible, but it's not overwhelming either. Somewhere in the middle, a coin flip. Perhaps the most telling comparison is with Comet Lovejoy, that death-defying survivor we mentioned earlier that passed just 87,000 miles above the Sun's surface 40 times closer than 3I/Atlas will get, and lived to tell the tale. Lovejoy was estimated to be about 200 metres across, roughly 1/10 to 1/5 the size of 3I/Atlas. It survived temperatures that should have vaporized it. How? Probably because it had a surprisingly solid core. Maybe a large rocky component providing structural support. Maybe just fortunate internal geometry that distributed stress evenly. Does 3I/Atlas have similar advantages? Or is it more like those comets, Ison, linear? Others that looked solid until perihelion proved otherwise. The telescopes watching right now aren't just passively observing, they're actively hunting for the telltale signs sudden brightness changes, the appearance of secondary condensations in the coma, changes in the dust emission pattern, spectroscopic signatures of freshly exposed material. Any of those could be the early warning that fragmentation is beginning, that millions of years of structural integrity are about to end in a matter of hours. But even if 3I/Atlas holds together, even if it survives perihelion intact, there's still the question of what we'll actually see. What data we'll be able to capture during those crucial hours when observation conditions are most challenging. There's a cruel irony in observing comets at perihelion. The moment when they're most interesting is also the moment when they're hardest to see. Think about the geometry for a second. 3I/Atlas is approaching the Sun from our perspective here on Earth. At closest approach, that critical moment we've been counting down to it will be roughly 31 million miles from the Sun's surface. That sounds far, but in astronomical terms, it's intimate. The Sun appears 47 times larger in 3I/Atlas's sky than it does in ours. And from Earth's perspective, the comet will be positioned just 24 degrees away from the Sun's glare in our sky. For reference, that's about the width of an outstretched hand at arm's length. Try looking at something that close to the Sun. Go ahead, imagine it. You can't. The Sun is 400,000 times brighter than the full moon. Its light scatters through Earth's atmosphere, creating a blue glow that washes out everything nearby. Professional telescopes have filters and careful positioning to block direct sunlight, but even they struggle with objects this close to solar glare. For several hours around closest approach, 3I/Atlas will be effectively invisible from the ground, hidden not by its own faintness, but by our star's overwhelming brilliance. This is why timing matters so desperately. The useful observation window is narrow, roughly 36 hours before perihelion and 36 hours after. That's it. Before that, the comet is still approaching, still heating up, not yet at maximum activity. After that, it's receding, cooling down, and whatever drama happened at closest approach is already over. Everything astronomers hope to learn about fragmentation, about outbursts, about compositional changes has to be captured in that 72-hour window, with a several-hour gap right in the middle when observations are impossible. Dr. Matthew Knight, who we've mentioned before, has coordinated what he calls the 3I/Atlas perihelion campaign, a global effort involving more than 30 professional observatories and countless amateur astronomers. The campaign's observation schedule reads like a carefully choreographed dance. As the comet moves across the sky, observatories in different time zones hand off coverage like relay runners passing a baton. It starts on the morning of December 18th with telescopes in Hawaii, the Gemini North Observatory, and the Canada-France-Hawaii telescope on Mauna Kea. They catch 3 Ice/Atlas low on the eastern horizon just before dawn, taking spectroscopic measurements to establish a baseline of activity. As the sun rises in Hawaii and observation becomes impossible, the Atacama Large Millimeter Array in Chile takes over. Using its unique capability to observe during daylight hours, radio telescopes don't care about blue sky the way optical ones do. By evening of December 18th, telescopes in South Africa and Australia join in. The Southern African Large Telescope and the Siding Spring Observatory capture high-resolution images of the coma structure, looking for any signs of jets, streamers, or secondary condensations that might indicate fragmentation beginning. As Earth rotates and those sites lose visibility, observatories in Europe pick up the watch, the Very Large Telescope in Chile, the William Herschel Telescope in the Canary Islands, the Nordic Optical Telescope. Then comes the gap. On December 19th, from approximately 9 a.m. to 6 p.m. Universal Time, 3 Ice/Atlas is too close to the Sun for ground-based telescopes to safely observe. This is when the space-based assets become critical. NASA's Solar Dynamics Observatory, which normally stares at the Sun 24/7 monitoring solar activity, has been reprogrammed to watch for 3 Ice/Atlas's passage through its field of view. SDO orbits Earth in a geosynchronous position, always facing the Sun, equipped with instruments that can block out the solar disk while still seeing the surrounding corona. If 3 Ice/Atlas passes through SDO's field during those critical hours and predictions suggest it will, we might get images of the comet at the exact moment of closest approach. Something that's only been achieved for a handful of sun-grazing comets in history. The European Space Agency's solar orbiter is in an even better position. Unlike SDO, which stays near Earth, Solar Orbiter is currently about 40 million miles from the Sun on its own elliptical path. From that vantage point, 3 Ice/Atlas and the Sun are separated by a wider angle enough that Solar Orbiter's cameras can image the comet without the same glare problems Earth-based telescopes face. ESA has allocated 4 hours of observation time on December 19th, using Solar Orbiter's ultraviolet and visible light images to capture what should be the highest resolution images of 3 Ice/Atlas at perihelion. But there's uncertainty even here. Solar Orbiter's pointing is limited. It can only look in certain directions without risking damage from solar radiation. If 3 Ice/Atlas's trajectory is slightly different than predicted, even by a degree or two, it might pass outside the spacecraft's safe observation zone. Mission planners won't know for sure until the day before whether the geometry will work. Then there's the James Webb Space Telescope, the crown jewel of modern astronomy. JWST can't look anywhere near the Sun. Its delicate infrared instruments would be fried by scattered sunlight. But in the days after perihelion, as 3 Ice/Atlas begins to recede and the Sun-Comet-Earth angle widens, JWST has been scheduled for a 6-hour observation block starting December 21st. Those observations will target the mid-infrared spectrum, looking for heat signatures from dust grains, measuring the temperature distribution in the coma, searching for organic molecules that only show up clearly in infrared light. The coordination required for all this is staggering. Each telescope has its own scheduling system, its own priority proposals, its own technical constraints. Getting them all to focus on a single target during a narrow time window required months of planning, coordination meetings across time zones, and in some cases, emergency directors' discretionary time, the astronomical equivalent of a fire alarm that lets you cut to the front of the line. And it's not just professional observatories. Amateur astronomers around the world have been mobilizing too. The Amateur Comet Observers Network, a loose collaboration of hundreds of experienced comet watchers, has set up a shared database where anyone can upload their observations. Images, brightness measurements, positional data, spectroscopic readings from those who have the equipment. It all goes into a central archive that professional astronomers can access in real time. During Comet Sun's approach in 2013, amateur observations actually provided critical early warning that the nucleus was disintegrating, hours before professional telescopes could confirm it. Michael Jaeger, an Austrian amateur astronomer who's been photographing comets for 30 years, has positioned himself at a dark sky site in the Austrian Alps specifically for the 3W/ATLAS campaign. His setup, a 12-inch telescope with a high-sensitivity CCD camera, rivals what professional observatories had just a generation ago. For objects like this, Jaeger said in an interview with Sky and Telescope, you need continuous monitoring. Professional telescopes observe for an hour, then move to another target. Amateurs can stay on one object all night, catching short-term variations that big telescopes miss. But even with all this coordination, all this technology, there are things we simply won't be able to see. The nucleus itself, for example. Even the Hubble Space Telescope, with its sharp vision, can't resolve 3I/Atlas's nucleus at this distance. A 2-kilometre object at 150 million kilometres, the current distance appears about 0.003 arc-seconds across. That's like trying to see a basketball from 6,000 miles away. What we see is the coma, that cloud of gas and dust surrounding the nucleus, which is thousands of times larger and easier to observe. But the coma is just the symptom. The real story, the structure, the composition, the fractures or lack thereof is hidden inside a shroud we can't penetrate. We also won't know the rotation rate with certainty. Light curve analysis can give hints, but without resolved images of the nucleus, we're essentially guessing based on brightness variations. A fast rotating nucleus would show regular periodic changes. A slow rotating one, or a tumbling one, would be harder to characterize. And rotation matters for fragmentation risks spin too fast, and centrifugal force helps pull the object apart. There are also blind spots in the data. No telescope observes continuously in all wavelengths. Optical telescopes see visible light. Infrared telescopes see heat. Radio telescopes see molecular emission. UV telescopes see highly energetic processes. To get the complete picture, you need all of them observing simultaneously. And that's impossible. There will be gaps, moments when something significant happens, but only 1 or 2 telescopes are watching, limiting what we can infer about the cause. Dr. Colin Snodgrass, who leads the European effort, put it pragmatically, we'll get great data, the best we've ever gotten for an interstellar object at perihelion, but we'll also be left with questions. That's how science works. You answer some mysteries and uncover new ones. The reality is that December 19th isn't an ending, it's a beginning. A beginning of years of analysis, debate, modelling and interpretation. The observations being made right now will keep astronomers busy well into the late 2020s, as they cross-reference spectroscopic measurements with fragmentation models, compare compositional data with theories of planet formation, and argue about what the isotopic ratios really mean about 3I/Atlas's origin. But for now, in these final hours before perihelion, the focus is simpler watch, record, don't miss anything, because this is it. This is the one chance. 3I/Atlas will never be this close to the Sun again. After perihelion, it will begin the long acceleration back toward interstellar space, fading from view over the course of months, eventually becoming too faint for even the largest telescopes to track. By mid-2025 it will be gone, lost against the background stars, headed back into the cosmic dark. But before it goes, before it slips away forever, there are still questions that need answers, questions not just about what 3I/Atlas is, but about what it represents, what it might mean for our understanding of how common these visitors really are. There's a moment in every major astronomical discovery when the data stops making complete sense, when the straightforward explanations don't quite fit, and scientists start entertaining ideas they wouldn't normally say out loud. Not wild speculation, they're too careful for that, but thoughtful what-ifs that push against the boundaries of conventional thinking. 3I/Atlas has created several of those moments. Let's start with the least controversial wildcard theory. the one that's actually appeared in peer-reviewed papers 3I/Atlas. Might not be a comet at all, at least not in the traditional sense. When the Rosetta spacecraft spent 2 years studying Comet 67P up close. One of its most surprising discoveries was just how dark the surface was. Not grey, not brown, black. The nucleus reflected only about 6% of the sunlight hitting it, making it darker than charcoal, darker than most asteroids. One of the darkest objects in the solar system. That darkness comes from complex organic compounds, those tholins we mentioned earlier, coating the surface like tar. But underneath that dark crust, Rosetta found something unexpected. The nucleus was extremely porous, with a density only slightly higher than cork. About 80% of its volume was empty space voids, cavities, gaps between loosely compacted ice and dust. It wasn't a solid iceberg floating through space. It was more like cosmic foam, a structure so fragile you could probably push your hand through parts of it if you weren't wearing a spacesuit. What if 3I/Atlas has an even more extreme structure? What if its interior is almost entirely void space? Just a thin shell of ice and rock surrounding a hollow core. This isn't as crazy as it sounds. Dr. Nalin Samarasinya at the Planetary Science Institute has modelled how such structures could form during the early stages of planet formation. As dust and ice grains slowly accumulate in a protoplanetary disk, they don't pack together efficiently. They stick where they touch, creating a framework with lots of gaps. Over time, more material fills in some gaps, but not all. The result is a hierarchical structure, solid in some places, hollow in others, with cavities ranging from millimeters to potentially meters across. If 3I/Atlas has large internal voids, that would explain several puzzles. The October outburst could have been a cavity collapsed the roof of a subsurface void giving way, suddenly exposing buried volatile ice to sunlight. The irregular brightness variations could reflect sunlight penetrating through thin sections and heating interior pockets at random intervals. Even the elevated carbon monoxide could make sense. CO ice trapped in internal cavities would be protected from sublimation, preserved over millions of years while surface layers eroded away. The downside? A highly porous structure is also a highly fragile one. Perihelion might not gently heat it, it might cause cascading internal collapses as one cavity failure triggers others. Think of a honeycomb being crushed. It doesn't break cleanly. It crumples progressively until nothing solid remains. Then there's the binary theory. What if 3I/Atlas isn't one object, but two, a contact binary where two separate nuclei are barely touching, or even a separated binary where two objects orbit each other at a distance of just a few kilometers? This happens more often than you'd think. Comet 67P, that same object Rosetta studied, is almost certainly a contact binary, two distinct lobes connected by a narrow neck, like a cosmic rubber duck. The New Horizons spacecraft discovered in 2019 that the Kuiper Belt object Arrokoth is also a contact binary. Two separate objects that gently merged early in solar system history. And several near-Earth asteroids are known to be separated binaries, with a small moonlet orbiting a larger primary. For 3I/Atlas, a binary structure would explain the erratic activity patterns. If the two components have different compositions, one more volatile rich, one more stable, they would respond to solar heating differently. As they rotate around each other, first one would be active, then the other, creating seemingly random variations in brightness and gas production that don't match simple rotation models. Dr. Petr Pravec, an asteroid researcher at the Czech Academy of Sciences who specializes in binary systems, has noted that roughly 15% of near-Earth asteroids are binaries. There's no reason to think interstellar objects would be different, he remarked in a 2023 review paper. If anything, the gentle ejection processes that send objects into interstellar space might preferentially preserve binaries that would be disrupted by more violent events. The challenge with this theory is observational at 3I/Atalus's current distance. Even Hubble can't resolve two separate nuclei if they're only a few kilometers apart. The only way to confirm a binary would be through very precise light curve analysis, looking for the telltale double peak pattern as two objects alternately occult each other. Some researchers claim to see hints of that pattern in the November data, others say it's just noise. If 3I/Atlas is a binary, and the two components are only weakly bound held together by mutual gravity that's barely stronger than the disruptive forces from solar heating and tidal stress perihelion could pull them apart, we'd go from observing one object to suddenly tracking two, each following slightly different trajectories as they diverge over the following weeks. Now, let's venture into slightly more speculative territory, the artificial structure hypothesis. Before you roll your eyes, understand that no serious scientist is claiming 3I/Atlas is an alien spacecraft, but several researchers have pointed out that some of its characteristics are consistent with what an artificial object might look like. And in science, you're supposed to consider all hypotheses that fit the data, even uncomfortable ones. The argument goes like this. Oumuamua, that first interstellar visitor, had a highly unusual shape and showed non-gravitational acceleration that was difficult to explain with standard comet outgassing models. Several papers, including one by Harvard astronomer Avi Loeb, suggested that the acceleration pattern was more consistent with a light sail, a thin reflective sheet pushed by solar radiation. That doesn't mean it was a light sail, but the data fit that model better than the alternatives. 3I/Atlas shows different anomalies, the barely hyperbolic orbit, the elevated sodium emissions suggesting unusual composition, the activity patterns that don't match normal comet behaviour. Could those collectively indicate something other than a natural object doctor, Beatrice Villarroel at Stockholm University, who studies unusual astronomical transients, put it carefully in a 2024 interview? We should be open to the possibility that not every unidentified object is natural. The universe is 13.8 billion years old. Technological civilizations could have arisen and fallen countless times. Their artifacts might still be drifting through space. That said, extraordinary claims require extraordinary evidence, and we don't have that evidence for any object yet, including 3I/Atlas. The more mundane explanation, and the one most scientists favour, is that 3I/Atlas is simply a comet from a planetary system with different formation conditions than ours, and its unusual characteristics reflect that alien origin, not an artificial one. The sodium could come from a parent star with higher metallicity. The orbit could be a statistical fluke. The activity could reflect a composition we're not familiar with because we've only studied objects from our own solar system in detail. But here's what makes the artificial hypothesis impossible to completely dismiss. We can't visit 3I/Atlas. We can't land on it, drill into it, analyse its structure directly. All we have are measurements from millions of miles away: brightness, spectrum, trajectory, and those measurements, while improving with each observation, have inherent limitations. You can't definitively prove something is natural from a distance, any more than you can definitively prove it's artificial. Carl Sagan had a principle for exactly these situations. Extraordinary claims require extraordinary evidence, but the absence of evidence is not evidence of absence. In other words, just because we haven't found proof of artificial objects doesn't mean they don't exist, but we shouldn't assume they do exist without compelling reason. For 3I/Atlas, the compelling reason would be something unambiguous: a radio signal, a geometrically perfect structure visible in high-resolution images, acceleration patterns that couldn't possibly be explained by natural processes. None of those things have been observed. The default assumption remains that this is a natural comet, however unusual its properties might be. Perhaps the most intellectually honest position is the one taken by Dr. Michelle Bannister at the University of Canterbury, who studies small body populations across the solar system. 3I/Atlas is teaching us that our sample size of interstellar objects is still way too small to know what's normal. We've seen three. You can't establish statistical patterns from 3 examples. Maybe 3I/Atlas's characteristics are rare. Or maybe they're common and we've just been unlucky with our small sample. That's the real wild card. We don't know what we don't know. Every interstellar object that passes through our solar system expands our understanding, but it also reveals new mysteries, new questions we didn't know to ask. Oumuamua showed us that interstellar visitors can be shaped like nothing we've seen before. Borisov showed us they can carry familiar chemistry across light years. 3I/Atlas is showing us. Well, we're still figuring that out, and we're about to learn a lot more, because the countdown has reached its final hours. Whatever 3I/Atlas is, pristine comet, fragile rubble pile, binary system, or something we haven't even considered perihelion is about to force it to reveal itself. The telescopes are ready, the observers are watching, the data recorders are running. But once perihelion passes, once those critical hours are over, and 3I/Atlas begins its long journey back to interstellar space, what then? What happens to all this data? All these observations, all these questions. December 20th, 2024, perihelion has passed. 3I/Atlas has survived its closest encounter with the Sun and is now beginning the long journey back toward the outer solar system. But the story isn't over in many ways. It's just beginning. The first question astronomers ask isn't what did we learn? It's simpler, is it still there? That might sound obvious. But remember Comet Ison. On November 28, 2013, Ison entered perihelion as a solid object roughly a mile across. NASA's Solar Dynamics Observatory captured images of it approaching the Sun, passing behind the solar disk, and then emerging as a faint smudge. For a few hours, there was hope maybe it had survived. Maybe that smudge would brighten as material sublimated from a battered but intact nucleus. Instead, over the following days, that smudge faded into nothing. The nucleus had been completely vaporized. What emerged from perihelion was just a dispersing cloud of dust. No solid core remaining. So when 3I/Atlas emerges from the solar glare on December 20th and telescopes in Australia and South Africa pick it up again, the first measurement is brightness. If it's roughly as bright as models predicted, accounting for the expected increase in activity from perihelion heating that suggests the nucleus is intact, if it's dramatically brighter, that could mean fragmentation has exposed fresh surface area, increasing the active area, pumping out gas and dust. If it's dramatically fainter, that could mean the opposite, catastrophic disintegration into pieces too small to be very active. Let's game out the three scenarios and what each would mean for science. Scenario 1. Clean survival 3. I/Atlas emerges intact, slightly brighter than before perihelion, but showing no signs of fragmentation. The light curve settles into a predictable pattern. Spectroscopic measurements show elevated gas production for a few days as the heated nucleus slowly cools. Then activity gradually declines as it moves farther from the Sun. This is actually the most scientifically valuable outcome in some ways. An intact nucleus means the data we gather over the following weeks represents a single, coherent object. We can track how its activity evolves as it cools, measuring the decay rate of different gas species. Water vapour, which sublimates easily, will decline quickly. Carbon monoxide, with its lower sublimation temperature, will persist longer. By measuring those decay curves, astronomers can infer the temperature gradient within the nucleus, how deep the perihelion heating penetrated, how quickly heat is radiating back into space. Dr. Yanga Fernandez at the University of Central Florida has spent years studying comet thermal evolution. In a 2022 paper on post-perihelion behaviour, he noted that the cooling phase is when we learn about internal structure. A porous nucleus with lots of voids will cool faster than a dense, solid one. A large nucleus will retain heat longer than a small one. The post-perihelion activity curve is essentially a thermometer that tells us what's happening inside. For 3I/Atlas, those measurements would be unprecedented. No interstellar object has ever been observed through a complete perihelion passage and cooling phase. We'd be watching, in real time, how an object from another star system responds to thermal stress we can quantify precisely. That data would anchor models of comet structure for decades. There's also the trajectory to consider. Perihelion passages change orbits not dramatically for distant passages like Thrion/Atlas S, but measurably. The intense outgassing acts like tiny rocket engines, pushing the nucleus in ways that slightly alter its path. By precisely measuring 3I/Atlas's post-perihelion trajectory and comparing it to predictions, astronomers can calculate the total momentum transfer from outgassing. That, in turn, tells them the total mass of gas and dust released, which constrains the nucleus size and composition. Scenario 2 controlled fragmentation. 3I/Atlas splits into 2 or more large pieces, let's say 3 to 5 major fragments each, at least several hundred meters across. They remain relatively close together, within a few thousand kilometers, all following nearly identical orbits. This scenario turns one object into a small fleet, and each fragment becomes an independent data point. Are they similar in composition, or do they show differences that reveal chemical heterogeneity in the original nucleus? Do they have different rotation rates, suggesting the original object was spinning fast enough to preferentially shed material from its equator? Do some fragments show more activity than others, indicating they contain more volatile material? History shows that fragmented comets can teach us extraordinary things. When comet Shoemaker-Levy 9 split into 21 pieces before hitting Jupiter in 1994, astronomers got to study 21 different cross-sections of the same object. Some fragments were dense and dark, suggesting they came from the interior. Others were bright and fluffy, likely from outer layers. The fragment diversity revealed that the original comet wasn't homogeneous. It had structure, layering, compositional gradients. If 3I/Atlas fragments, each piece would have slightly different cooling rates based on its size and composition. Tracking those differences would be like doing a CT scan of the original nucleus, revealing its internal architecture from the behavior of its broken parts. There's also a practical benefit fragment spread out over time, expanding the observation window. While a single intact nucleus would fade beyond detectability by mid-2025 as it races back toward interstellar space, a trail of fragments would remain visible longer. Some pieces might still be trackable in late 2025 or even 2026, giving astronomers months of additional data. Scenario 3. Catastrophic disintegration 3I/Atlas completely falls apart into hundreds or thousands of pieces, most too small to track individually. What remains is a dispersing debris cloud similar to what happened with Comet Linear in 2000 or ISON in 2013. This sounds like the worst outcome, but it's not without scientific value. Even a debris cloud tells a story. First, the very fact of disintegration reveals something about structural strength. We can calculate the stresses 3I/Atlas experienced at perihelion thermal, tidal rotational. If those stresses exceeded the object's ability to hold together, that sets an upper limit on its material strength. For an interstellar object, that's valuable data. It tells us whether comets from other star systems are fundamentally similar to ours. Same strength, same structure, or fundamentally different. Second, debris clouds evolve in predictable ways. The smallest dust particles get pushed outward by solar radiation pressure, creating an expanding shell. Larger fragments continue along the original orbit, spreading out over time due to small velocity differences. By tracking how fast the cloud expands and disperses, astronomers can infer the size distribution of the debris, how many boulder-sized chunks, how many pebbles, how much fine dust. Dr. Zdenek Sakanina at JPL, whom we mentioned earlier, has made a career of studying disintegrated comets. His models can take the debris cloud morphology and work backward to reconstruct what the nucleus must have looked like before breakup. The debris pattern is a fingerprint, he explained in a 2015 paper. Each fragmentation event leaves a unique signature in how the material spreads. From that signature, you can infer rotation rate, fracture patterns, even whether the breakup was sudden or progressive. For 3I/Atlas, A debris cloud would also give us one last gift spectroscopy of freshly exposed interior material. When a comet disintegrates, material that was buried deep inside suddenly gets exposed to sunlight. Ice that's been shielded for millions of years, possibly billions, suddenly starts sublimating. The spectroscopic signature of that interior material might be different from what we measured before perihelion, less weathered, more pristine, closer to the original chemistry of the protoplanetary disk where 3I/Atlas formed. NASA's JWST observations scheduled for December the 21st would be crucial in this scenario. Webb's infrared eyes could detect warm dust in the debris cloud, measuring temperature distributions that reveal how recently material was exposed. Hot dust means recent fragmentation. Cooler dust means the breakup happened hours or days earlier, and the material has had time to radiate heat away. The long game. Regardless of which scenario unfolds, the real work begins after the observations end, when 3I/Atlas fades from view whether as an intact nucleus, a fragment train, or a dispersing cloud. Astronomers will be left with terabytes of data to analyse. That analysis will take years. Spectroscopic data needs to be carefully calibrated, cross-referenced with laboratory measurements of ice and dust properties. Compared with models of comet chemistry, light curves need to be fitted with rotation and outgassing models. Trajectory measurements need to be refined using all available data to constrain the mass and activity patterns. Papers will be published. Conferences will be held. Graduate students will write dissertations on specific aspects of 3I/Atlas's behaviour. And slowly, over the course of the late 2020s, a consensus will emerge about what this object was, where it came from, and what it taught us. But there's one question that analysis can't answer, one uncertainty that will persist no matter how much data we gather. When will the next one arrive? How long before another interstellar visitor swings through our solar system, carrying new mysteries and new opportunities? The statistics suggest we should see one every few years. But statistics are built on small samples, and our sample is still vanishingly small. We've confirmed 3 in 7 years. That could be the normal rate. Or we could have been lucky. The next visitor might arrive in 2025, or 2035, or not until the next century. What we do know is that everyone matters. Every observation refines our understanding. Every measurement helps us prepare for the next encounter. And that preparation and the lessons we take from 3I/Atlas might matter more than anything we've learned so far. Stand outside on a clear night and look up. Every star you can see, thousands of them scattered across the darkness, is a sun. And around many of those suns, perhaps most of them, orbit planets, some rocky like Earth, some gas giants like Jupiter, and around those planets, in the cold outer reaches of each system, drift billions of icy objects, comets, remnants of formation, cosmic leftovers that never quite made it into planets. Now consider the mathematics. Our galaxy contains somewhere between 100 and 400 billion stars. If even a fraction of those stars have comet populations like our own, and there's no reason to think they wouldn't, we're talking about trillions upon trillions of icy bodies scattered throughout the Milky Way, and gravitational interactions, close stellar encounters. The slow drift of orbits over millions of years, all of these processes constantly eject some fraction of those comets into interstellar space. The result is a galaxy filled with wanderers. Objects like 3I/Atlas, drifting between the stars, carrying chemistry from their birth systems, moving slowly enough that they'll take millions of years to cross even a tiny fraction of galactic space. They're everywhere, invisible until one happens to pass close enough to a star, our star to be caught and studied. When you think about it that way, 3I/Atlas isn't a rare visitor. It's a sample, one data point in an almost infinite population. And that's why it matters so profoundly. The panspermia question. There's a hypothesis in astrobiology that makes some scientists uncomfortable, not because it's implausible, but because it's so difficult to test. It's called panspermia, the idea that life, or at least the building blocks of life, might spread between star systems via objects exactly like 3I/Atlas. Think about what we know comets contain: water ice, organic molecules, amino acids. When NASA's Stardust mission analysed samples from Comet Wild 2 in 2006, it found glycine the simplest amino acid, one of the fundamental building blocks of proteins. That glycine formed in space, in the cold chemistry of the protoplanetary disk, before Earth even existed. The building blocks of life aren't exclusive to Earth. They're cosmic. Now imagine an interstellar comet, perhaps one ejected from a system where life already exists, carrying not just organic molecules, but actual microorganisms. Bacteria, for example, can survive extreme conditions. Some species tolerate radiation doses that would kill a human 1,000 times over. Others can remain dormant for millions of years, essentially frozen in time, waiting for conditions to improve. Could hardy microbes survive a multi-million-year journey through interstellar space, embedded in ice, shielded from cosmic rays by meters of rock and frozen gas doctor? Gerda Horneck, a pioneer in studying extremophiles in space conditions, conducted experiments aboard the International Space Station exposing bacteria to vacuum, radiation, and temperature extremes. Some species survived for years. Not all cells, but enough. Life, she concluded in a 2010 review paper, is more robust than we typically assume. If microbes can survive interstellar travel, and if interstellar comets regularly pass through planetary systems like ours, then life might not be isolated to individual worlds. It might be, in a sense, a galactic phenomenon spreading slowly, randomly, wherever conditions allow. Earth's life could have originated here, or it could have been seeded by an ancient impact from an interstellar visitor that arrived billions of years ago, long before humans evolved to notice such things. 3I/Atlas won't answer that question definitively. We're not going to detect life on it. We don't have the tools to look for biosignatures from this distance. And even if we did, the chances of this particular comet carrying life are astronomically small. But every interstellar object we study teaches us whether the chemistry necessary for life is universal. Are complex organic molecules common? Are amino acids everywhere? Or rare? Do different star systems produce different biochemistry? Or do the same reactions happen everywhere given the same starting materials? The more comets we study, the better we understand whether Earth's life is a cosmic accident or an inevitable consequence of universal chemistry. The planetary defense angle. There's a more immediate reason to care about interstellar objects, one that has nothing to do with the origins of life and everything to do with protecting the life we already have. On February 15th, 2013, a 20-metre asteroid entered Earth's atmosphere over Chelyabinsk, Russia. Travelling at 19 kilometres per second, it exploded at an altitude of 30 kilometres, releasing energy equivalent to about 500 kilotons of TNT, roughly 30 times the Hiroshima bomb. The shockwave shattered windows across the region, injured over 500 people, and served as a stark reminder that space isn't empty and Earth isn't invulnerable. The asteroid came from within our solar system, following a predictable orbit that, in theory, we could have detected and tracked. Now imagine an object like Oumuamua but larger, and on a collision course with Earth. By the time we spotted it, it would be moving at 26 kilometers per second, approaching from a direction we weren't monitoring because we don't expect threats from interstellar space. We'd have weeks, maybe months, of warning instead of years. Our current planetary defense strategy is the careful tracking of near-Earth asteroids. The plans for deflection missions assume we'll see threats coming with plenty of time to react. Interstellar objects break that assumption. Dr. Kelly Fast, who manages NASA's Near-Earth Object Observations Program, addressed this concern in a 2019 briefing after Oumuamua's discovery. Our detection systems are optimized for objects in bound orbits around the Sun. They make repeated passes, so even if we miss them once, we'll catch them the next time around. Interstellar visitors don't give you a second chance. You either detect them on their way in, or you miss them entirely. The good news is that the odds of an interstellar impact are vanishingly small. Space is vast. Earth is tiny, and even with trillions of interstellar objects drifting through the galaxy, the chances of one hitting us in any given year are essentially zero. But essentially zero isn't the same as zero. And understanding interstellar objects, their composition, their structure, their behaviour helps us prepare for the scenario, however unlikely, where one does pose a threat. If 3I/Atlas is porous and fragile, that tells us an interstellar impactor might break up in the atmosphere, reducing ground damage. If it's dense and solid, that suggests atmosphere breakup is less likely and impact energy would be delivered more efficiently to the surface. These aren't idle questions. They're parameters that go into impact models that inform evacuation plans, deflection strategies, and risk assessments, the philosophical dimension. But perhaps the deepest reason 3I/Atlas matters has nothing to do with practical applications or specific scientific questions. It has to do with perspective. For most of human history, the night sky was static. The stars were fixed points, eternal and unchanging. The planets wandered, that's what planet means, wanderer, but they stayed within predictable bounds. The universe, as far as anyone could tell, was orderly, stable, comprehensible. Then telescopes revealed the truth. Everything moves. Stars drift through space at hundreds of kilometers per second. Galaxies collide and merge over billions of years. The universe expands, carrying distant galaxies away from us faster than light can bridge the gap. Nothing is static. Nothing is eternal. And now we've confirmed what astronomers long suspected: the space between stars isn't empty. It's populated with wanderers, objects ejected from distant systems, carrying with them the chemistry and history of worlds we'll never see. 3I/Atlas spent millions of years crossing the void, survived a close encounter with our sun, and will spend millions more years travelling onward, perhaps eventually encountering another star system, perhaps drifting forever through the cosmic dark. We are witnesses to a moment in that journey. For a few weeks in late 2024, this visitor from beyond passed close enough for us to study, and we turned every available telescope toward it, capturing data that will be analysed for years to come. We asked questions, we made measurements, we learned something about the universe beyond our immediate neighbourhood, and the act of observing, measuring, trying to understand is itself profound. We're a species that looks up. We notice the wanderers. We track their paths and wonder where they came from. We build machines to see what our eyes cannot, to detect light our brains cannot process, to measure distances our intuition cannot grasp. 3I/Atlas doesn't care that we're watching. It's not putting on a show for our benefit. It's simply following the laws of physics, responding to gravity and heat and radiation in ways dictated by its structure and composition. But we care. We're curious. And that curiosity, that drive to understand the universe, not because it's useful, but because there might be the most remarkable thing about being human. Carl Sagan, in his book Pale Blue Dot, wrote about the photograph of Earth taken by Voyager 1 from the edge of the solar system. Everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives on that mote of dust suspended in a sunbeam. That perspective, seeing ourselves as small, temporary, part of something vastly larger, doesn't diminish us. It elevates us, because we're the dust that learn to look outward. We're the ones asking questions. 3I/Atlas reminds us that our solar system isn't isolated. We're part of a galactic ecosystem connected to distant stars by these wandering messengers. Every few years, one passes through. Each one teaches us something new, expands our understanding, raises questions we hadn't thought to ask. And somewhere out there, right now, the next visitor is already on its way. We don't know when it will arrive. We don't know what it will look like or what mysteries it will carry, but we know it's coming because the galaxy is vast and ancient and full of worlds, and some fraction of those worlds send their orphan children into the deep. When that next visitor arrives, whether in 2025 or 2050 or 2100, humanity will be ready. We'll have better telescopes, sharper instruments, more sophisticated models. We'll have learned from Oumuamua, from Borisov, from 3i/Atlas. Each observation refines our methods. Each measurement improves our understanding. We're learning to read messages written in ice and rock, sent from star systems so distant their light takes decades or centuries to reach us. We're learning the language of the cosmos, one vista at a time. And every time we successfully decode one of those messages, every time we extract meaning from the data and transform observations into knowledge, we're participating in something larger than ourselves. We're part of the universe trying to understand itself. And that might be the most important story of all.